Hello there. In this video we're going to be considering the particular problem of nested radicals. So nested radicals are ones of the form where you have a radical of something that also has a radical inside of it, which some people again refer to as nested radicals, right? So nested radicals. So understanding nested radicals sometimes can be a bit difficult. So what we like to do is decompose this nested radical in a more natural way, such as a radical plus integer or something along those lines, or sum of two radicals instead. So in this video we're going to discuss how to sort of analyze nested radicals to represent them in other ways that may be a little bit more useful to work with. All right, so we're going to be primarily working with the screw decomposition problem, and you can easily extend this to say 3 nested radicals or maybe a cube root, square root, fourth root type of composition problem if you want, but the analysis is going to be extremely similar. So we're going to be considering the general problem of the square root of a plus the square root of c. Right, and let us assume that this decomposes into the form x plus y times the square root of c, where x and y are some real numbers and c is some given positive real. Right, let's assume that. All right, so if this is the case, we can square both sides of this equation to give us a plus b square root of c is equal to x squared plus cy squared plus 2xy times the square root of c. And then we can construct a system of equations by equating both sides of this radical expression. So we can get this system, x squared plus cy squared is equal to a, and 2xy is equal to b, right? So this is the general system for solving problems like this, right? All right, so let's look at a particular case that is a slight generalization, but not the total generalization. And that is the case where a and b are both equal to 1, and c is greater than 1. So that means we're looking at something like 1 plus the square root of 2. So does there exist x and y such that this decomposes into this expression? So let us go through this expression proof. Well, it's not a proof because I haven't stated the theorem yet. So solving this last equation for y, we're going to get y is equal to b divided by 2x. And then we can substitute that into the first equation, and that's going to give us x squared plus cy squared is equal to a, to imply x squared plus cb squared over 4x squared is equal to a. We can multiply both sides of this equation by 4x squared, and that's going to give us the equation 4x squared minus 4a x squared plus cb squared is equal to 0. And then we can use a u substitution by letting u is equal to x squared because this is a quasi-quadratic equation, namely the one 4u squared minus 4au plus cb squared is equal to 0. Right, and that's the general quadratic for the general problem, right? So our assumption says that a and b both be equal to 1, and that's going to give us 4u squared minus 4u plus c is equal to 0. So we can look at the discriminant of this. So the discriminant is going to be b squared minus 4ac of the standard quadratic, right? So that's going to be equal to b squared minus 4a c, which in this case is c. That's cool. And that's going to be 16 minus 16c, which is of course equal to 16 times 1 minus c. So this is our general formula for the discriminant. So we see if c is greater than 1, that means the discriminant is less than 0. So that implies that u is going to be in c with the imaginary part of u non-equaling 0, right? So that means there does not exist x, y, and R2 such that the square root of 1 plus the square root of c is equal to x plus y square root of c for c bigger than 1. For c bigger than 1. Right? So that's pretty much the theorem that we're trying to prove here. So let's work through a numerical example to sort of see how to find such a thing. So let's let a and b not both be 1. For example, let's consider 2 plus the square root of 3. So we're looking for x and y such that this is true, right? All right, so let's go back to our general quadratic. So 4u squared minus 4au plus cb squared is equal to 0. All right, so a equals 2, b equals 1, and c is equal to 3. So that's going to turn this into 4u squared minus 8 times u plus 3 is equal to 0. So u is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, right? So we're going to get u is equal to, so what do we have here? So 8 plus or minus, so 16 times 4 is 64, so I can factor out a 16 out of that. So we're going to have 4 minus 3 all over 8, which is going to be 8 plus or minus 4 times the square root of 1 all over 8, and then we can divide 4 into each of those components. So u is going to be equal to 2 plus or minus 1 over 2. Right, so u is equal to 3 halves, and u is equal to 1 half. Right, so u is equal to that, or u is equal to that. So replacing back in terms of x, so that means x squared is equal to 3 halves, or x squared is equal to 1 half. So that means x is going to be equal to the square root of 3 halves, or x is equal to the square root of 1 half, right? Which implies x is going to be equal to the square root of 6 over, let's see, square root of 6 over 2, or x is equal to the square root of 2 over 2, right? And notice that I'm not considering the negative values of this quadratic equation, and you can sort of investigate on your own why I'm not considering those values. All right, so now I can consider the second equation. So recall that 2xy must be equal to 1. That's the second equation of the general system. So y is equal to 1 over 2x, right? So that means y is equal to 1 over 2 square roots of 6 over 2, which is 1 over square root of 6, which is root 6 over 6. Or y is equal to 1 over 2 times the square root of 2 over 2, which is 1 over root 2, which is the same as root 2 over 2, right? All right, so those are our pairs for x and y, right? So that means either xy is equal to root 6 over 2, root 6 over 6, or xy is equal to root 2 over 2, comma, root 2 over 2. Right? So now let's go back to the problem for which we're focusing on. So we're assuming that the square root of 2 plus the square root of 3 has the decomposition x plus y square root of 3, right? So I'm going to be choosing, I'll choose that one. So that means root 2 plus root 3 is actually equal to root 2 over 2 plus root 2 over 2 times root 3, which is the same as root 6 over 2, by the way. So this is going to be root 2 plus root 6 all over 2, right? So this nested radical expression actually decomposes into the sum of two simple irrational numbers, right? Which is sometimes, it depends how you look at it, a little bit more easier to work with. I also invite you to try and see that this actually generates the same exact answer. But this is pretty much a very easy approach that you can do for decompositions of radical expressions. You may want to, like if you have something like the square root of, like here's another type of structure, like a square root of b plus c square root of d, right? You may want to find numbers x and y such that this is true, right? So what is x and y that will make that true? And you can do this for all sorts of radical combinations. Anyway, that's just a brief introduction on how you can analyze nested radicals, whether it be two nested radicals, three, or possibly infinitely many. Hope you enjoyed.